Okay, so here you are, Ramzy Badawi.
Thank you so much. So I've actually got a couple of slides to show here. So just very briefly, really, just to follow on from what Dr. Morris says, welcome everybody to this symposium and all those people calling in remotely as well. So I'm just going to give a very brief sort of big picture view on this. We have 51 abstracts which we're presenting today. 46 of those were proffered, 5 of them were invited talks. And as we reviewed these abstracts, one of the things that really came out to me was just how outward facing this department is. So I went through the abstracts and just picked out a list of all the divisions and centers that have collaborators that on the abstracts that were submitted. And you can see here, there are 22 of them from the institution. And then I also looked at the external collaborators, and as you can see here, we have 8 or 9 institutions from across the country, about 10 institutions internationally, 5 companies, and that of course, that's not a limit to the number of people that we work with. It's just the ones that we have abstracts that were presented today. And we even have our own radiology startup that's represented here, and that's Dr. Lofelm's Panorad, and you'll hear more about that product a little bit later. So just getting on to some logistics here, we're going to have some invited talks between 3:10 and 4 o'clock. There'll be a coffee break between 4 and 4:15. There's coffee at the back there, and we'll be starting again at 4:15 sharp. Between 4:15 and 5:35, we have proffered talks. The talks are quite short so that we could get more in there. So there's 6-minute talks with 2 minutes for questions. And then after that, we thought we'd celebrate the excellence from the trainees. So we have some prizes for the trainees here. And then 5:40 food will be served outside, and that will be in conjunction with the poster session. Poster session 1 will run from 6 to 6:30, and poster session 2 from 6:30 to 7, and 7 is the close of proceedings today. There are electronic posters as well, and they will be available. You can view them. There's 4 workstations at the north end of the foyer where you can go and have a look at the e-posters. And they're also available from the website as well. So there's a QR code there and a website, and so you can have a look at the posters there. And there are a number of them that also have recorded presentations that go with that you can have a look at. The poster sessions, session 1 will be even numbered posters. And we had to make a move because of availability of the presenter. So poster 33 will also be presented in session 1. And then poster session 2 is the odd numbered posters except for 33. There's a poster map at the back end of the booklet that you should all have. And that will show you where everything is. There's only 20 posters, so it shouldn't be so hard for you to navigate. Then really it just remains for me to thank the people that made this possible. And there are actually really quite a number of people who really work very, very hard. And I particularly like to thank the local arrangements team that you can see here, who really worked very hard, put in lots of hours to make this work, above and beyond the call of duty, I think. And then I'd also like to thank these 3 down at the bottom here who stepped up when we needed help at the last minute to just make things happen. I'd like to thank our workstation support team who've done a fantastic job in sourcing and testing the workstations for the electronic posters. And you'll be able to meet them outside. They'll be looking after the workstations there. And also our microphone runners. So thank you, microphone runners, who are also here to help. And also, finally, the Scientific Programme Committee. All the abstracts that are presented today were all reviewed at least twice by the Programme Committee, and that helped us rank them, and it also helped us. They also did the prize selection as well. So thank you all so much for making that happen. And on that note, I will stop and invite our first speaker to the podium. And this is Dr. Audrey Fan. She is a relatively new faculty member in neurology and in biomedical engineering. She's a tremendous scientist, tremendous teacher, and a tremendous collaborator. And we've been working very, very closely with her, both in radiology and in biomedical engineering. Really looking forward to her talk. And microphone. Well, you've got to click on so you can.
Testing. Awesome. I'm honored to be here. In terms of the outward facing, as Ramsey introduced, I'm part of neurology and biomedical engineering, but I have an affiliation with radiology and really enjoy working with all of the faculty and student collaborators. Today, I'm going to look forward to a project that is being developed at the moment on bringing simultaneous PET-MR for the brain to UC Davis. And for those of you who may not have heard of simultaneous PET-MR, there are multiple whole body systems now where the gradient coils and the PET detectors are actually integrated together, as you're seeing in the MR board, enabling simultaneous scans of PET and MR at the same time. And so already seeing this sort of commercially available scanner, you can imagine it's easier for the patient if they have to get PET and MR to do it at once. There's nice co-alignment of images. With the MR, you are able to do some image corrections without a CT scan, so potentially reducing radiation dose. This is great. However, I think for brain especially, I think PET-MR can be leveraged for even more. And some of the things I want to cover in the first few minutes are just what really drives me in terms of using PET-MR simultaneously to look at things that are not just anatomy, but physiology with both modalities, and some insight into how we could extend this to kinetic modeling and also tracer delivery. So one example I like to give is in a stroke-related disorder called moyamoya. So neuroradiologists in the room will be aware that this disease has progressive steno-occlusions of arteries at the base of the brain, and these patients are at risk of stroke, 7-fold increase. And in these patients, it's helpful to understand the cerebral blood flow status. So what I'm showing here is a O15 water PET scan. It's literally water with radioactive labeling. And you can see this maybe diminished blood flow anteriorly in the circulation. This is helpful, but PET with O15 tracers only has a 2-minute half-life. And so it's really challenging to be able to do this in a clinical setting despite the utility to these patients. And if we wanted to take a stab at doing this with MR, something more non-invasive, and there's expertise with Dr. Youngkoo Chung in radiology and myself, specifically in arterial spin labeling, where radio frequency tags are applied at the neck level, and you try to get a cerebral blood flow map. And it's really through comparison simultaneously that we're able to validate this and say, hey, this is as good of a cerebral blood flow map for clinical use, but it takes a lot of careful rigor because as you can see, there's some heterogeneities, higher signal, lower signal, the tag isn't arriving or isn't transporting into the capillary space. There's a lot of discrepancies that over time, by doing these comparisons simultaneously, we're able to look on a group and say, okay, maybe the standard MR ASL has way more deficits than actually what the gold standard is with PET up here. And maybe we need to tailor our ASL MRI recommendations, for instance, with multiple delay times with ASL in order to do well for these patients, right? So that's an example of physiology and physiology comparisons. You may ask, like, is this really necessary to do simultaneously? And I would argue, yes, because if you're drinking some coffee to stay awake during my talk, your blood flow could decrease by like 30%. And especially if we do brain stress tests, like giving a vasodilation, just like a cardiologist might have you run on a treadmill. In this comparison, it's especially important to see, hey, can we actually create the same two physiological states, monitor them with both PET and MR, and do a validation not only at baseline, but also with a stress test. On top of this, I just want to touch on a couple of other studies that could extend on physiology in tandem with PET. So some of you may know amyloid is a plaque, a toxic deposition that happens in Alzheimer's disease and related dementias. And there are PET tracers that we can monitor with a static image or with full kinetic modeling for more quantification. But this usually takes a really long scan time. And so one of the things, if we have PET and MR, like a blood flow image during the MR scan, what you might be able to do is recapitulate the early delivery of the tracer and actually quantify amyloid plaques in a way that's better than a static SUV PET scan, and then ultimately use a shorter scan with both PET and MR to get quantitative amyloid calculations, potentially reducing the number of patients with dementia that we need to include in clinical trials. Okay, so these are just examples. I'm going to skip ahead, but I just want to clarify that there's things that if you know physiology, if you can monitor that simultaneously with MR and PET, the total of the two is greater than the sum of the parts. And so what does that mean for Davis? Well, what I'm really excited about is to bring this neuro-PET-MR to Davis. And there's a company called Cubressa in Winnipeg, Canada, that we're collaborating with, called Cubressa, and they already have an existing preclinical PET scanner called NuPET. What they are developing is the first PET insert for 3 Tesla MR. And here's another image of what it would look like mocked up. And the great thing, I see Dr. Cam Carter, the director of the Imaging Research Center, sitting there. He's been very supportive. This would actually slot into an existing research MR 3 Tesla and enable for brain PET MR simultaneously. And it's removable when you don't need to use it, and has high sensitivity and spatial resolution. So with this ongoing collaboration, we're at the early stages of discussing, but you'll recognize many of the faces here, usual suspects, but also great experts, right? So I'm so proud of this team that we're starting to assemble, because Cubressa is thinking of UC Davis as the technical site to test their new product. So why? We have so much experience, which you'll hear from Dr. Cherry later, in quantitative PET, especially at high count rates, new systems, new geometries. We can break the system and tell them how to make it more quantitatively accurate. We have hardware capabilities to enhance time of flight. And also with myself and Felipe, who's a relatively new faculty too, we have both MR and PET expertise. So with that, I also just want to touch on some of the clinical applications. The Cubressa team is really interested in dementia. So I'm part of the Alzheimer's Disease Research Center, and these patients are already, a subset of them are receiving amyloid and tau PET. And this is critical to characterizing both Alzheimer's and non-Alzheimer's related pathology that may lead to neurodegeneration. So I want to test the Cubressa brain PET, harmonizing it with other PET CTs that you have familiarity with in radiology. With Felipe, I want to understand, especially with high gradient demanding scans like diffusion or resting state, how do these two signals affect each other? And apropos to the kinetic modeling I was referring to, do better in terms of quantifying amyloid and tau with PET-MR. So I'm at the end of the talk, key points for neuro especially, and especially if you can look at blood flow or physiology. The whole is sum is more than the sum of the parts. Represented here are just a smattering of the key collaborations, the technical side as well as neurological applications. And the key point is that we are uniquely positioned, centering in radiology and these collaborations to technically evaluate, optimize, and show that brain PET is going to add value for dementia patients. Sorry. But thank you. That's the end of my talk. Happy to take any questions.
Wonderful. Thank you, Audrey. Do we have any questions for Dr. Fan? Anything from the chat there? Timescale, when do you think this might happen?
I'm hoping in like half a year or so that we'll get a system, but things are still in the works.
All right. Well,
Yep.
Thank you very much. Let's thank the speaker one more time.
Great, thank you.
And our next speaker is Dr. Tom Lofhelm. Dr. Lofhelm is an abdominal imaging attending, and he's also a coder. So that's a great combination to be a physician who's also a coder and natural language processing expert. And he's going to talk to us about some of his machine learning projects that he's been involved in. Tom, thank you.
Thank you, Ramsey. Great. Well, thank you, Ramsey, for the invitation to speak today, and thank you all for your attention. I'm going to talk about a program and a product that I've developed called Pathfinder. I have a disclosure. It is a commercial product. It's free to UC Davis, so I don't get any benefit from the use of it here, except just satisfaction. So in general, what we do with Pathfinder is we process all radiology and pathology reports basically in real time as they're sent across the system on their way to EHR or some of the other downstream systems. We get a copy of them in the Pathfinder application. So, and from there, we run them through a natural language processing pipeline, which basically translates the plain text reports into a series of annotations, where the annotations include information on what anatomy concepts are mentioned in what parts of the report, what disease things are mentioned, whether the disease is mentioned as being negated, present, or absent. So for example, you could read a CT and say that there's no appendicitis, or you could read it and say that there's appendicitis. So in both cases, you're mentioning the disease, but in one you're saying it's present and one you're not. And that's important for downstream use of that data. So that's the whole point to the application, is to take this data that's currently locked in plain text in our reports and put it into a format that's queryable, that's analyzable, and see what we can do with that. Everything is sort of translated from text into something called a CUI, which is a unique identifier for a biomedical concept. It's not something that we've come up with. It's a standard kind of part of the UMLS, the Unified Medical Language System. It's sort of the way that biomedical concepts are represented in structured data. And the advantage to doing that is that once you sort of base an annotation into some reference ontology, you get access to a lot of other information that's carried in that structure. So, for example, for acute pulmonary embolism, it gets annotated as one concept, but by looking into the UMLS and seeing kind of the relationships that has, you can determine what organ it's involved in. This isn't a great example for pulmonary embolism, but for cholecystitis, for example, you could understand that it's an acute inflammatory process or acute infectious process, that the gallbladder is involved. And so when you can tie concepts in a radiology report to that larger sort of organized data resource, you can start to ask a lot of interesting questions. So for example, you could query our radiology reports database and say, show me examples of acute inflammatory processes in organs in the abdomen and pelvis. Things like that are useful sort of questions for education, for just organizing the data that we generate in radiology and analyzing it. You get access to those layers of information by tying those annotations to a reference ontology. So again, everything gets sort of turned into an annotation. A given radiology report might yield 100 annotations in different parts of the report. We know what comes from the impression, what comes from the findings, whether the radiologist expressed uncertainty when they were describing it or not. So we've had this program up and running now for a year. We've got about 2 years worth of data loaded into it. We're coming up on 1 million exams, combination of radiology and pathology exams that are loaded. The sort of main use of it is to then determine linkages between radiology and pathology reports. So that was kind of the initial genesis of this program, is that it's useful to radiologists to know whatever happened with the thing that I described yesterday. So the gallbladder I saw yesterday and I thought it was cholecystitis. If that gallbladder comes out tomorrow, I have no way to know that unless I have a system like this that can tell me. So we create those RADPath matches from analysis of those annotation sets. So from nearly 1 million total exams, we've created about 140,000 RADPath matches, and those are based on 22 million individual annotations from the reports. So what I'm really interested in, though, for this talk, for research purposes, is what can you do with those 22 million structured annotations of radiology and pathology data? And I think you can do a lot. I think we're just kind of scratching the surface in coming up with these RADPath matches. but I think there's a lot of cool things in there. So you can start to think about new ways to measure radiology quality. You can start to think about ways to measure diagnostic yield. So of all the CT-PE exams we do, how often do we find pulmonary embolism? Do those practice patterns differ in the ER, or under what circumstances do they differ? Can you start to measure diagnostic accuracy of individual radiologists? That's a bit of a touchy subject, but I think if you can do it and you can show that it's useful, then it's probably something we should consider. And then at sort of more superficial or stylistic levels, you can get some information on just general reporting style. So does it matter if the radiologist lists 10 differential diagnoses in their impression, or if they just direct you to the next appropriate test? You can start to ask those questions and get some of those insights by analyzing such a comprehensive data set. I'm going to show you a couple of specific examples of what we can do. So CT positivity I mentioned specifically because it's sort of a clinically relevant question. And so this is the positivity rate for CT-PE exams ordered through our ER over the last several years. And we actually did this manually. So a resident and I went through the impressions of all 7,000 of those reports and flagged them as whether the radiologist said there was a PE or there wasn't a PE. And as you can see, our rate is pretty constant over time. And I wanted to know then, how does our NLP system match to that? And it turns out there's differences. If you watch the individual dots, there's differences, but the overall average is about the same. So what we can do then is, by analyzing these NLP annotations, we can look across our entire radiology history and get a sense for how our CT-PE ordering yield is. That might not seem too interesting at first, but if you know that about a year ago we implemented at kind of great expense, at great clinical expense, at great cost, we implemented a decision support tool in the ER to hopefully improve the diagnostic yield of CT-PE studies. So the whole rationale for this decision support system is that we're over-ordering PE studies in the ER. Well, if that's true, then when you implement a CDS tool, you should get rid of some of the inappropriate orders. You should keep the orders that were appropriate, and you should see a higher test positivity rate. And as we can kind of determine now automatically and at large scale, we basically had no effect on that. Now, that's not necessarily bad news. I think really one way to look at that is that we're already doing a really good job here. And so we didn't need the additional support of a decision support tool. But the way that the CDS program is rolled out, there's no mechanism for that built into it. So everybody has to go through the clicks and the form to determine if their order was appropriate, even if we can show that doing all that extra work, including all that extra expense, doesn't lead to any downstream outcome. So I think this is an example of the sort of interesting insight you can get by doing a large scale, by having the sort of insight into your radiology data at scale. We can do a couple other interesting things, and I'll just touch on these. This is a little bit more of a sensitive topic, but how about among individual radiologists? Do they differ in their accuracy? Even when using a standardized assessment tool like PI-RADS, which is supposed to be objective, it's supposed to guide you through your analysis with kind of specific criteria, and you end up at a likelihood of malignancy in the prostate gland. So even applying that and looking at our different radiologists here, we vary. Somebody that says PI-RADS 5, which is the highest likelihood of cancer, when those prostates go to biopsy, they find cancer 100% of the time. Another radiologist, they find it 60% of the time. Why is that? I'm not sure. What should you do about it? I'm not sure. Again, it's touchy to start to pick out individual radiologists and say, you're performing at a different level than your colleague. And there's lots of reasons that people come back and explain why they might be different. But I think unless you look at it this way, you can't even begin to ask those questions or think about ways that we could improve that. But I think if you can show that there is that difference in accuracy, that it's important. One other cool thing that we can do that's sort of interesting. So PI-RADS is kind of easy because we're assigning a specific score in our reports, and pathology is too. I wanted to try to use this for generalized diagnostic accuracy, and cholecystitis is sort of interest to me. So I've done projects before where I wanted to look at what our accuracy is for diagnosing acute cholecystitis from right upper quadrant ultrasound. And that's easily a 3-month project in terms of getting the data, reviewing it manually, scoring it. And what we can do though with this system is do it kind of in real time. And so this is literally real time of looking at ER and inpatients, looking at our limited right upper quadrant ultrasound exams, finding cases where there's pathology within 10 days of the radiology exam. And I want to look at acute cholecystitis specifically. And so when I do that, I'll go through those report annotations. I know from that UMLS ontology that cholecystitis occurs in the gallbladder. So I know to look for pathology reports that are of the gallbladder. And in like literally 20 seconds, you can look through all of our reports and get back those times. And you could find cases where the radiology report was positive and the pathology was negative or vice versa. You can get an idea of what the overall accuracy and sensitivity is. And again, this is a 3-month project to do manually, and it's 20 seconds to do if you have access to a tool like this. So I think it really enables interesting insights into what we do. It's a really interesting data resource and allows us to ask questions of what we're doing and measure what we're doing in ways that we can't otherwise. I want to give special acknowledgement to Abdullah Khan, one of our R3 residents, who's going to be presenting some of this work at RSNA this year.
Thank you, Dr. Lofam. That was a really, really interesting talk, and I'm sure there are lots of questions, but unfortunately, in the interest of time, because we've got so many presentations this afternoon, we'll have to curtail questions until the break. Perhaps you can talk to Dr. Lofam offline. So our next presenter is Dr. Osama Raslan from the Neuroradiology Division. So Dr. Raslan is a multi-talented physician, and he's got a particular interest in 3D visualization. And he's got a really, really interesting talk. I can't wait to hear it.
Can you hear me back there? Thank you so much, Dr. Badawi and Dr. Morris, for the kind invitation. Today I'm going to talk about UC Davis's medical 3D printing lab, and the name is 3D Print Viz Lab. These are my disclosures. We're going to talk a little bit about what is 3D printing, some applications that we have here, touch about augmented reality, some of the challenges that we face, and some frequently asked questions. A couple of years ago, Dr. Edwards from Pediatric Neurosurgery reached out to radiology to help with a very complex case of conjoined twin separation. Specifically, he wanted to visualize the intricate anatomy joining the twins in order to plan for a safe separation. We went to work, and using virtual and 3D printed models, we were able to bring these venous connections joining the two twins, as shown here in yellow, to life. With the help of augmented reality model, the surgical team was able to simulate the surgery. And here we can see our neurosurgeons, Dr. Edwards and Shalea, discussing the venous connections and seeing it from every possible angle and discussing where exactly to place the surgical clips. This model also helped Dr. Edwards to train his more than 30 surgical team members so that every member of the team knows exactly what to do during this surgery. During the surgery, the twins required 5 changes in position. And using the 3D printed models, the surgeons can reference these models and immediately reorient themselves to the new appearance of the surgical field. Working on the same case, Dr. Wang from plastic surgery had a different challenge. He wanted to know where exactly to place his skin incision, and also to estimate the size of the skin defect resulting from the separation to be able to cover this defect. Using 3D printed, we created a custom model for these twins, which can switch back and forth before and after twin separation. The model also included the tissue expanders, in which he simulated the amount of skin needed to cover this defect. And using this, Dr. Wang was able to accurately predict the size of the skin needed to cover the defect. Seeing what impact this has done to our patients and our institution as a whole, there's no doubt that establishing this service was an integral part of any forward-looking radiology service. So what exactly is 3D printing? It's a process by which a material is fused and deposited to form complex 3D structures. There are different technologies that we can use depending on, what's our aim for that. This is, for example, SLA, where you have gooey material that's sintered with laser. There is material jetting, just like the polyjet that we are used to, and then there's more advanced powder metal, which is sintered together to form the object together. We can also print in different consistencies, hard like bone, soft, like firm like the ear lobule, very pliable like this cardiac model here that they were testing, placing Platzer plugs, and very intricate geometry, as you can see here. We can also use coloring for a better illustration. Since its introduction in 1986, 3D printing application has made its way into many industries, including aerospace industry, which is just like medicine, requires consistency and reliability as well. By the 2000s, it made its way into the medical field. As I speak to you, there's a crown in my teeth that was 3D printed at my dentist's office, and I watched it as it's being printed. So that's amazing. Looking at the industry as in general, it's predicted that 3D printing in medicine is almost $2 billion industry by 2022. There's also an explosion in the research arena as well. As you can see here, by searching in PubMed, about 5,000 papers last year about 3D printing. So what are some of the applications for 3D printing? There are clinical applications. We're going to talk about some education for the trainees and for the patients, prototyping and creation of medical devices, and bioprinting. In the clinical arena, 3D printing is fast becoming a standard of practice and in many specialties, and the demand is only increasing. Here at UC Davis, and with the help of Dr. Ahmed Reza, we have a strong collaboration with cardiology and pediatric cardiology in these models. We also have a standing relationship with ENT surgeons, helping them to reconstruct the mandibles and bones after tumor and trauma reconstruction. And we're hoping to jump into manufacturing surgical guides, which will help these surgeons basically fill the jigsaw of changing a fibula into a reconstructed mandible, basically. With the help of Dr. Pillay, we are working closely with Dr. Sadia and his common cloaca surgeries. And this is a quote from his comment about the use of 3D printing, is that he was able to change his approach from mobilization to separation. The difference between these two approaches is vast, both on time and complexity. So we're happy we achieved that result as well. So to sum up the clinical applications, we provide personalized preoperative planning. This is a study that was done on renal cancers, 3D printed renal cancers, and they printed 10 models, and all the 10 models, the approach was changed based on these models. Also physical simulation, and it's kind of akin to flying by the seat of your pants versus an autopilot. Which plane would you like to be on? There are studies showing minimized blood loss, decreasing length of the surgical incision, in addition to thousands of dollars of savings in OR time. If we know that in California here, 1 minute of OR time is about $37. This study also showing a saving of about $4,000 for 3D anatomic models and about $1,500 for surgical guides. It also can help in choosing the appropriate prosthesis. In the arena of education of trainees, it goes without saying, looking at the 3D anatomy is much more intuitive than looking at the 2D images. This is one of the studies that tested that, and it showed improved the first medical student assessment of renal tumors and coming close to expert surgeons in their evaluations. This is showing molds for breast cancer and simulation and robotic surgery as well. As for the education for patients, it's very hard for our patients to understand these 2D images, the CTs and the MRIs. So imagine if it's much more intuitive to show them a 3D model, and this naturally will basically reflect on the satisfaction of the patients. In fact, that was proven by the study in which they showed 3D models of cerebral aneurysms for a group versus a group that didn't see that. And you can see a huge difference in the Likert scores for the satisfaction of the service. Similar things were done also for the breast models as well. 3D printing can be also used for prototyping and creation of medical devices, such as this splint, basically, that was used to open up a bronchial stenosis. We can use it for personalized chokers and introducers and anti-reflux valves. And the area also can be used in bioprinting, which is an exploding field right now as well. As a byproduct of in addition to the physical model, we also get the virtual model, which can be used to simulate the surgery. It can be also fused with the pathology to help to guide the surgeons during his laparoscopic approach to achieve the best results. A few of the challenges that we're facing, like any new technology, there's skepticism at the cost of starting and running the labs. Currently, there's low reimbursement, but hopefully with the help of the National 3D Printing Registry, will become a fully reimbursed service, and of course, some regulations and rules. Our website is on the UC Davis site. The way to order prints is basically through the form. And we get an email, and then we work with you through the different processes to get the 3D printed model. A very commonly asked question, the cost. It highly depends on what are we printing, but in short, it's much less than what industry will use. We are located at the Oak Park building, and there are plans to switch also to the Aggie Square space as well within the 3D printing lab over there. So we're in-house. We have the technology, and we have the only FDA-approved software. We have the BME experience through our strong collaborators with us, and the subspecialty radiologists. We also have AR capabilities and less cost than other industry. So thank you so much for that. I'm sorry if I run out of time, but just to leave you with this message, as a radiologist, we're doing an excellent job in diagnosis and therapy. However, part of our service is visualization that the surgeons need to see what we are showing them. So with the help of 3D printing and augmented reality, hopefully that will bring the scale back to balance. Because together with AI, I think this is how any radiology department will look in the future. Thank you so much. These are my collaborators in the lab.
Thank you again for a just really exciting talk, and that was such a compelling use case that you started off with, and really brilliant. Unfortunately, again, we are a bit pressed for time, so questions to Dr. Raslan at the break, if possible. And then let's move on to our next talk, and our next speaker is Professor Simon Cherry, Distinguished Professor in Biomedical Engineering and in Radiology. He is one of the giants in the field of molecular imaging. And we're looking forward to hearing his talk, which will be about some of the industrial collaborations we've been doing here at UC Davis.
Well, it's great to be here. A wonderful event. Great to see so many faces again. Some people I haven't seen in a couple of years or so. So today I briefly want to talk about how we can leverage the strengths of academia and industry to advance the field of imaging and develop next generation imaging systems. And particularly, this has been a central theme in the molecular imaging program here at UC Davis. And I'm going to give you a couple of examples of what we've done. So first of all, let's talk a bit about the ingredients that can make for a successful academic industry partnership. So in academia, we're often generating new ideas, new technologies, new algorithms. We obviously understand what the applications may be for these technologies, and we have a lot of know-how. Then within industry, there's great expertise in manufacturing and engineering, or the regulatory aspects of bringing a new imaging device online, knowledge of the market, and ultimately, if we're going to have an impact through our academic ideas, we've got to be able to disseminate the technology as well. And of course, they play a crucial role in that part. So to be successful, you've got to bring all these things together. And some of the key pieces are you've got to have a shared vision. You've got to have goals that are aligned. There has to be a fair amount of trust, because often to get things moving, you're actually going to be a little bit ahead of all the paperwork that's going to come with it. And so there has to be some trust to make that happen. You've got to deal with the tricky issues of IP and licensing and revenue sharing. And you've got to think about how you're going to fund this. And this is, again, where academia can bring something to bear, because we often have access to funding sources that can help jumpstart a project with a company that might not want to initially invest their own money at the very beginning. And of course, we have a great example of that here at UC Davis, which I hope everybody in this room by now has heard about, which is the development of the total body PET scanner, the Explorer scanner, which was the first medical imaging device that could image the entire human body all at once. And Ramsey and I had a concept, which is shown on the top there, and 15 years later, there's a commercial product, which is shown on the bottom. So a little bit about the timeline. Actually, the first 10 years or so was spent convincing our community and our funders that this was a good idea. But once we got funded, which happened in September of 2015, things moved incredibly quickly because we had an industrial partner. Modern PET scanners are incredibly complicated devices, large numbers of components, and this is really something as an academic lab we cannot do on our own. So we partnered with a company called United Imaging Healthcare for this project. And we had our first meeting with them. They came to UC Davis to present some concepts of how they might approach this project in December of 2015. And we went to visit them in Shanghai to do a site visit the following January, just a month later. So this kicked off the project, and we set out a number of milestones and a stepwise approach to reaching our goals. The first thing we asked them to do was actually to build a mock-up of the system, so we could study some of the workflow issues. There were some concerns about claustrophobia that we wanted to look at. And also was just a test to see that the company could deliver something on the time scale and to the quality that they were saying they would be able to do. So that was delivered in November of 2016. We then asked them to build a small scale prototype so we could evaluate the technology, take some measurements. That was called the Mini Explorer. And that was delivered here in January of 2018. And I should mention that the fate of some of these systems, so the mock-up is now in the new Museum of Science and Curiosity in Sacramento. So you take your kids there, it's a great museum. You can see the mock-up sitting there. The Mini Explorer is now installed in the School of Veterinary Medicine here at UC Davis, and is being used both for clinical and for research studies there. Concurrently, as we were testing the Mini Explorer, they started work on actually building the full Explorer scanner that took place over about 8 months. And the scanner was completed by May 2018. First human imaging was done locally in Shanghai in August of that year. FDA 510(k) clearance, which was important for us because we wanted to use the system clinically, was obtained in December of 2018. The system was then shipped here. There was a little issue with tariffs, which I can tell you about over coffee if you wish. And then in June of 2019, we did our first research scan and our first clinical scan in August of that year. Incredibly, from first meeting to first clinical scan at UC Davis, under 4 years. Just amazing. Absolutely impossible without an industrial partner. So, of course, having this system was great, but it also seeded an entire program here at UC Davis. So just to give you some of the numbers, we're already at over 2,000 clinical scans, over 300 research scans. We have 20 different IRB protocols currently running, 10 different radio tracers, 15 different PIs using the center, and that's only going to grow as more grants get funded. Lots of different research areas. You'll see in some of the following presentations and in the posters outside, some of these represented. But this system really has very, very broad applications. The educational opportunities are not lost on us either. So we're trying to build training programs and educational opportunities around the system and this idea of whole body systems research. We've already graduated our first 2 biomedical engineering students who based most of their thesis work on the Explorer system. and there'll be plenty of more coming. We're engaged with pharma and biotech to use the system. So we have a number of companies that are engaged with us and sponsoring in one way or another studies on the system. And I think it's been great from an institutional perspective. It's brought a lot of visibility to UC Davis in various forms. Whether you prefer the citations to the peer-reviewed papers or the views on YouTube is up to you, but it's had a lot of visibility. And we've really built now a very nice translational total body imaging program here at UC Davis because, as I mentioned, we have the Mini Explorer that's at the School of Veterinary Medicine. Of course, we have the Human Explorer here in Sacramento. And the Mini Explorer actually was then commercialized by the company as a system for large animal imaging. And the Primate Center got a shared instrumentation grant to put a system in there. It was just installed a few weeks ago. So they also have a Mini Explorer for non-human primate imaging. So with this very nice translational platform, we add in the small animal facilities at the Center for Molecular and Genomic Imaging that's directed by Dr. Chowdhury. We can really go from small animal to large animal to human, total body systems research. A lot of great opportunities there. And then there's the broader impact beyond the institution. So these are commercial systems. This is a big advantage of working with a company. There's now 13 of these total body human scanners installed and 3 of the smaller scale systems installed across the world. It's also generated competition amongst the vendors. So Siemens now have what I'll call a half body scanner because it's 1 meter in length rather than the 2 meters that ours is, but still covering a large extent of the body. We know GE are also developing a system, not quite sure what that's going to look like yet. So now we have multiple vendors in the field, and you can see this whole concept really taking off. If you look at publications or citations, you see this exponential growth now, and this concept after 15 years is finally taking off. And one of the nice things that we've been able to do with our data is we've been able to share it with lots of other institutions as well. So here's just a selection of the institutions that already have access to some of the data that we've taken. So if you make a blockbuster movie, you make a sequel, right? So here's the daughter of Explorer called the Neuro Explorer, where we really decided to take the lessons from the Total Body Explorer system, but now focusing on the human brain. It was motivated in part by the fact there hadn't been a dedicated brain system, PET system developed for about 20 years, at least not a commercial one. And so this was a partnership between Yale University, who were the lead on this project, UC Davis, and again, the same company, United Imaging Healthcare. And the goal here was to really focus on detection sensitivity. That's always the challenge in nuclear medicine, PET imaging, is getting enough counts to get high signal-to-noise ratio images, particularly in the brain where we also want to do fast dynamic imaging and good quantification. But we also want high spatial resolution to look at small structures. So we put a proposal together that was funded by the NIH Brain Initiative. We're now in the 2nd year of that proposal. And the UC Davis PI is Jinyi Qi out of biomedical engineering. So this system will be about 50 centimeters in length, about 50 centimeters across. Has a unique design in that it has a shoulder cutout, which allows us to get the shoulders right up against the scanner, but the brain deep into the scanner where we have high detection sensitivity. We also hope to be able to image the carotid arteries to get the radiotracer input function into the brain, which would be important for our kinetic modeling studies. Here are some photographs of the system under construction. It's almost complete at this point. Again, it's a very complex system, something we could not have built in-house. So again, illustrating the importance of working with industry. And a broad range of interesting applications that we're interested to look at in collaboration with Yale. And this system will have about a 10-fold higher sensitivity than existing commercial systems. And it will be a commercial system, so again, will be broadly available. And although Yale will be getting the initial prototype, we would very much hope that we'll find a way to bring one of these systems to UC Davis as well. The final point I want to make is to do these kinds of large-scale projects takes a lot of people. And I'm sure I've missed some people off here, in which case I absolutely apologize. We've had a large team at UC Davis working on the Total Body Explorer system, illustrated here, but also a large engineering team at United Imaging. That photograph shows all the people at the company who were involved in helping build that system. And the same for the Neuro Explorer project. Again, a large team, This is mostly the academic team rather than the engineering team that's involved across the three institutions, the two academic institutions and the company. And I want to give particular credit to Stan Majeski, who really pushed us to pursue this idea of a dedicated brain system, and Jinyu Chi, who's leading the UC Davis team to develop the system. So exciting times ahead with this new system coming online. We should be seeing first images, I suspect, by towards the end of this year. So look out for that. And with that, I'll stop, and thanks for your attention.
Thank you, Simon. I'm looking at the time. We're actually running 10 minutes late, so we're not going to do questions here. Simon can be caught at a break. So instead, I'd like to invite my colleague Felipe Godinez up to the podium. Dr. Godinez is also a relatively new faculty member in radiology. He has expertise. He's a physicist. He's got expertise in PET and MRI instrumentation. And he also has a passion for engaging with the community. And that's what he's going to be speaking about today.
Thank you, Ramsey, for that. And Dr. Morris, thank you for the invitation. I feel very honored and privileged to be here speaking to you about this topic. So I'll talk about what I've learned and the experience I've had and what I think might be something to look forward to within the Department of Radiology, and of course can expand beyond with regarding to how do we use our position as biomedical engineering research or biomedical imaging researchers, because radiology in the end is the application, right? It's the delivery of a service that was designed, and we're part of that design process. And how do we use our position to help eliminate health disparities? So my hope is to demonstrate the value of community in doing this, and to keep always, and to help us understand that there's real world impact of certain factors in people's lives that can change their healthcare. And we can probably influence some of them. And finally, I want to give some examples of what has been done here at UC Davis within the department as well. So I'll just bring back some experience that I've had from back in 2010 as a PhD student here at UC Davis through the organization that I was part of, still a member of, the Association of Professional Students. A group of students who were not yet professionals, still going to school, got together and put together a health fair. And I was one of the co-organizers. Our goal was to build a bridge. At the time, we were very naive of what this meant, but we understood that within our community, there was a need for a bridge from the needs in health to reaching healthcare. In the process, what we did is we developed trust with the people who went to this health fair, allowing them to, for example, get their blood sugar level measured, something they probably wouldn't have done at a hospital because they don't tend to do that normally. Many of them discovered that maybe their health was really good, or maybe they had some issue, some problem that they had to attend to. Started to look at this process of removing barriers by having the younger community look at these healthcare givers or individuals who represented the medical fields more as people that they can reach to, they can talk to. And then I think a very important one, inspiring the young, the future health professionals within these communities that could take a stand in the future to help address these issues. So this was me being very ignorant about what health factors or social economic factors are that influence health. In preparing this process, in preparing this talk, I started to really focus on these factors, and I started to find out that, in fact, there's so many things that if we can put a label on that actually change the course of someone's healthcare. From having transportation to not having transportation, from having able to understand or read the literature that can educate them about their healthcare, communicating with their physicians, or even having one, childcare, and the list goes on. Right? We can all look at some of these and identify someone in our community that we know is living something like this. And the real truth is that these factors vary by race and ethnicity. It doesn't, not everybody experiences it the same way. And that's one of the things that, as someone like myself growing up in, say, for example, the Mexican community or the Latino community, you see things that, for example, uncles and aunts who don't go to the doctor, and that's normal. You don't realize that there's a problem there, because when they do go to the doctor, it's because that's the end of it. There's no there's no cure. And so you get this idea that going to the doctor is a bad thing. And you can only go to the doctor when you're really sick. And if someone does go to the doctor, it's because something really bad really happened. And so there's a list of reasons why people don't go. So I found this really cool paper that described how radiology can play a role and what role we play in helping meet the gap, right? Close the gap in these health disparities. And I found a story that I put a name on the person that the story is about. I call her Rebecca, because that's the name of my youngest daughter. And I want to make sure that I understand that what happened to this person in the story, I don't want it to happen to my daughter. And so the story is about a 60-year-old uninsured Black woman. And I have some pictures here of individuals who are actually real people who have, if you do a search on the internet, you'll find articles. And they're either cancer survivors or individuals who advocate for people who are experiencing this disease. And so Rebecca, being 60 years old, they found a focal asymmetry with mammography at one of these free health fairs. The same thing that I did as a student, someone did at her church, and she was able to learn something about her health that was very important. She tried to schedule an ultrasound in her closest radiology department, and it was very challenging for her to do because she does not have an open work schedule. She works 10 hours a day, and she does not have paid sick leave. So when she did get the appointment eventually, she traveled 2 hours by bus and presented herself at her appointment 45 minutes late, very unfortunate for her. And even though she tried very hard to keep herself from being sent home without her scan, she couldn't get it because the staff was adamant that there were other patients that had to be seen. So they told her to reschedule, and that would be very challenging for her to do. So 9 months later, when she ultimately gets the scan, they found an abnormal axillary lymph node. And what's the sad part is that the radiologist who was a member who did the biopsy later commented, she cannot believe that some women failed to take responsibility of their own healthcare, making Rebecca sound like an irresponsible individual. She was diagnosed with stage 3 breast cancer. And this is where the story ends. But what the story really highlights is that this is a real world case. And look at everything that's in bold here. These are all factors that can influence a person, whether they get an ultrasound or they don't get an ultrasound. So what can we do? First of all, we must recognize that there's this gap. And as researchers, figure out how we can fix this. So in radiology, everything seems to be black and white, right? The images don't have any color. And we think that radiology is agnostic to this, but it's not. In fact, still there's a great health impact here that's associated. And I point out there's 3 steps here that radiology performs to be able to serve a patient. Well, first there needs to be an indication, a question. A doctor needs to say, let's get the scan going. Once that happens, the scan, of course, or the imaging procedure takes place, and then there has to be a diagnosis. At every one of these steps, these factors can influence the outcome of the patient's health. So I'll take, for example, the pre-procedure step. Here's some data showing where patients who went to the emergency rooms throughout the United States, where they counted how many patients that visited the emergency room got a diagnostic imaging. And you can see here for white patients, there were the percentage of them that got diagnostic imaging is much higher than for patients who were non-white. So this already demonstrates a very large disparity between these 2 groups. So if someone went to the emergency, they might not get the imaging that is required for their diagnosis. The next step that might, another example is, for example, at the procedure level. And in this case, I'll talk about an example of interventional radiology. Here's another study that showed that if patients that experienced a large vessel ischemic stroke, if they were Black or Native American, they were less likely to receive an endovascular thrombectomy. And so this is a case where the utility of radiology is omitted in a certain group or less likely to benefit a certain group. So these examples motivate that we must act as a group to affirm this change. And what can we do? Well, let's start from the beginning. Let's start with those who can change their generation. And this is the young people of our community. We can talk to them and develop in them the motivation and inspire them to seek STEM degrees so they could be in the position to affect policy and affect change, to foster the diversity and inclusivity, to help bring professionals from these communities to actually carry out the research and put the issues that they're interested for their communities to the forefront of research and policy change. Provide education, which I think this department has done very well, to remove individual biases. And then the very most, I think, basic one is to engage with the community. Give them an opportunity to sit at the table and tell us how they feel, what they think is important to them, and what are the needs, so that everybody gets an opportunity to guide research. And this develops trust, it provides education opportunities, and it gives them advocacy. So here's an example of someone that I've been working with very recently. This is Fatima. She is actually a sophomore from UC Davis High School. And I've been working with her on a project because she came to us. She came looking to work with on something related to engineering. And she wrote this little thing in an email she sent me. She says, I always wanted to be a doctor or a healer, and I'm starting to realize that this can mean so many different things. I'm grateful to get a chance to learn about one of these paths, medical engineering. So this is a student who is very talented, who could be anything she could probably dream of, and she wants to be somewhere in the healthcare. Well, we can invite her and motivate her to find a career path that leads her into radiology. But finding her was not easy. Or it took a team of people. So Stan Majeski was the first person she made contact with, because her Fatima's father is his mailman, or delivers his mail. And Stan reached out to Dr. Badawi, who then reached out to myself. And I said, sure, let's see what we can do. And we figured out that I had this really interesting project that she can work on from home without having to come to UC Davis, because that's a barrier at the moment. And so I gave her an opportunity to study, or to help me program a function to look at different guide wire trajectories so that we can study them in the EMR field. So Fatima is doing really well, by the way. And what I didn't say about her is that during the pandemic, she spent her time learning how to code 6 different languages. So it's individuals like this that we need to recruit. We need to engage with and find opportunities for them to join us very early on. The other project is what's been done here around the Explorer project, again, to engage with the community, because the Explorer project brings so many benefits and it can change the lives of so many. And this is a project that was done with the different resources that are available here at UC Davis. For example, the Office of Community Outreach and Engagement, the Cancer Center's Community Advisory Board, and the Biomedical Technology Program that is here. And their goal is to basically bring community and basic clinical science together by allowing individuals from the community, stakeholders from the community, to experience the technology themselves and then talk about it and share that information to the people they know. And they did this through different media outlets. So this is the pathway that they followed. And what I want to highlight from this slide is that this pathway is a little treacherous, right? It's not very straight. There's a lot of things that have to be put in order to make this happen. And so our research is already complex as it is. Adding a layer of community engagement can make it even more complex. But I'm telling you that this will benefit our research and benefit the community both together. In the end, they ended up with 32 advertisements over radio, 11 TV interviews and newscasts. And the real result here is that they had 155 inquiries from the community to be able to participate in this research. To me, that is worth gold. So in conclusion, I think what we have here is a very clear goal, and that is that we can influence, we can change the health disparity gap. And there's so many ways to do it, and we all can come up with our own way to do it, but there's some ideas already out there that we can put in action. And then UC Davis is rich in resources, I think, and culture to do this. So thank you for your attention.
Fabulous talk, Dr. Godinez. That was excellent. Any questions for Dr. Godinez? Not seeing any in the chat. Yes, Jerry.
Yeah. Are there plans to reach out to the Sacramento High School?
Sorry, can we just repeat that to the microphone?
Hi, I'm Jerry Bushberg. Are there any plans to reach out to the Sacramento neighborhood high school to engage in future projects? And if so, how would that happen?
Yeah, we have had many conversations about this. There are talks. The idea has been floated. And in fact, one of my objectives as being a new faculty here in the radiology department is to actually begin a program that helps these young kids become part of our department from a satellite position, per se. But yes, we do hope to engage the community locally here in Sacramento. And I think to do it, there'll be two ways to do it, or two things need to happen. One of them is, as researchers, we need to put together showcase examples. And then we need to have a permanent program in place to be able to constantly be monitoring the outcome and the engagement with these schools, because one time isn't enough. It has to be a continuous effort.
All right, I'm actually going to pause things there. We're running exactly 15 minutes late. Rather than a 15-minute break, we'll take a 10-minute break. So we will reconvene here at 4:25, just enough time for a bio break and perhaps some of you to grab a coffee. So thank you very much. Let's thank the speakers from session one.